We've proved the existence part of the fundamental theorem. A natural number greater than 1 is either a prime or has a prime factorization. We now have to prove that each such prime factorization is, in fact, the only prime factorization. To help us, we'll first establish this small but useful intermediate result. Please read it carefully, and we'll continue when you are sure you understand what it says. Does anyone care to summarize this result?
It says that if a number is one of the prime divisors of a number, then it's one of the prime divisors of the number, which seems totally stupid.
I agree. I don't see why we have to prove something that's obviously true.
I see. So if it's obviously true, then I suppose it's completely trivial for you to prove it?
That's right. It's totally, utterly, completely trivial, as Amit will now demonstrate.
Actually, I don't think it's all that obvious. Plus, it doesn't say that Q is one of the numbers in the product. It's more like if you multiply a list of primes and you get the answer, then if Q is a divisor of the answer, then it must have been one of the primes in the list.
Emmy, that's an excellent analysis. As it turns out, this isn't completely trivial to prove, but given your skills, I don't think you will find it too difficult. Does the statement give you a clue as to how we might proceed in this proof?
I think by induction on n, if n is 1, then the list only contains one prime, so probably that prime has to be Q. But if there's more than one prime in the list, then maybe we could use the induction hypothesis.
Sometimes with induction proofs, it's worth just trying, and even if it fails, you will learn something that may later help you. So let's make a start and see how it goes. Emmy?
We proceed by induction. So the base is that Q is a divisor of the product of one prime. So the only prime is P sub 1?
That's right. The product is just P sub 1, so Q divides P sub 1.
So Q divides P sub 1, but P sub 1 is a prime, so its only divisors are 1 and itself. And Q is a prime, so it's not 1. So Q must be equal to P sub 1?
Emmy, that's excellent. If a prime number Q is known to divide a prime number R, then Q and R must be the same number. So now for the induction step. We let M be a natural number. What do we take as the induction hypothesis?
So for the induction hypothesis, if Q is a divisor of the product of m primes, then Q is equal to one of the primes.
Correct. That is, there is some I between 1 and m such that Q is equal to the ith prime.
So do we now suppose Q is the divisor of a product of m plus 1 primes?
Exactly. We suppose Q is a divisor of the product of the primes P sub 1 through P sub m plus 1.
I don't see what to do next.
We could try to split off the P sub m plus 1.
Maybe use Euclid's lemma?
I'll look that up in the index. Let's see. U for Euclid.
Euclid starts with an E.
I get it. So the product is just the product of the first m primes times P sub m plus 1. So by Euclid's lemma, either Q divides the product of the first m primes or Q divides P sub m plus 1.
Very good. Q divides the product, which we can write like this since we know multiplication is associative. And so, by Euclid's lemma, either Q divides the product of P sub 1 through P sub m, or Q divides P sub m plus 1.
Okay, so if it divides the product of the first m primes, then the induction hypothesis says that it's one of those m primes. And so case 2 is that Q divides P sub m plus 1, but then Q and P sub m plus 1 are both prime, and Q divides P sub m plus 1, so they must be the same prime.
Excellent. So in both cases, you have shown that Q is one of the primes p sub 1 through p sub m plus 1, and together with the base, the induction proof is complete. Well done. In the text, you'll find a formal proof of this useful result. Read it carefully, several times if necessary, and then we'll finish the proof of the fundamental theorem of arithmetic.
Found it! Euclid's lemma. If Q is a prime that divides x times y, then either Q divides x or Q divides y. Does that help?
Come on, Ron. We've got some reading to do.
So, do we need it?